Gate is the control terminal. So what we are doing in this experiment is we are constructing AC voltage controller using triac, and the control signal to triac is generated using a device called as diac. Is diac a control device or uncontrolled device? See, what all questions I am asking to you, you try to remember these questions or note down somewhere, because these are the very important Viva questions when it comes to this experiment. Okay, if there is if you have Viva on this experiment, you are going to expect, or you are going to get all these questions as Viva questions. First thing is, what is AC voltage controller? How can you construct AC voltage controller? When you go for track based AC voltage controller, when you go for SCR based AC voltage controller, why it's called as track and diac combination? Because the control signal given to track we are going to generate using diac. So this combination we are using, so it is called as using track and diac combination. Now diac is a controlled device or uncontrolled device? Is diac a controlled device? Diac is a uncontrolled device. What is difference between diac and diode? Diode is also uncontrolled device, right? What is difference between diac and diode, Rishikesh?
Ma'am, AC ma'am, diac is for alternating current.
Track is for alternating current, diode is for DC current.
Think so.
As the name says, it is DIAC is the diode for alternating current. Okay, but
Yes.
when we tell when we ask like what is the difference between diode and diac, you should not tell like the diac is for AC, the diode is for DC. You should tell in terms of its characteristics. Like diac is a bidirectional device, diode is a unidirectional device. Okay, that means diac allows current to flow in both the directions. Diode allows current to flow only in one direction. Okay, this is how you can tell the difference between diac and diode. Okay, diac is a bidirectional current uh, conducting element. Diode is unidirectional current conducting element. And one more important question is, what is the full form of track? What is full form of diac? Track full form is triode for alternating current. Triode in the sense three terminal element. Okay, triode for alternating current. Diac means diode for abbreviation for diac is diode for alternating current. Okay, the difference between SCR and triac is SCR conducts only in one direction. It is a unidirectional current conducting current handling capable device. Triac is bidirectional current handling capable device. Both are control devices. Same way we have diac and diode. Diac is a bidirectional current handling capable device, and diode is unidirectional current handling capable device. Okay, and both are uncontrolled devices. So what we are going to do in this experiment, we are going to conduct, or we are going to perform AC voltage controller for R load as well as for RL load. Okay, we are going to turn on the circuit. We are going to observe the voltage across resistance, voltage across RL load. If it is R load, voltage waveform across load, current waveform through the load. Current we are not going to observe because we don't have current measuring equipment in lab. So we are going to only observe the voltage across the load when it is R and when it is RL load. So the first objective of this experiment is to turn on triac using diac. So the first thing is we have a control circuit. Using that we are generating a control signal, and using the control signal we are turning on the track. This is the first aim of this experiment. Next, to vary the illumination of incandescent lamp by varying the RMS voltage using AC voltage controller. Okay, here incandescent lamp represents which load? What are the two loads that we are going to check in this experiment? R and RL load. Now, incandescent lamp belongs to which load? R can be modeled as which load?
R load.
R load, because incandescent lamp indicates heating and lighting. So heating can be indicated with R element, resistive element. So in this, the second point is we are going to connect AC voltage controller to a R load, that is incandescent lamp, and by varying the RMS voltage, we are varying the control pulse. We are varying the firing angle given to track. Thereby, the output RMS voltage across the AC voltage controller will be varied, and thereby the illumination of the incandescent bulb will be varied. Okay, the brightness will be increased and decreased. You can view physically as the RMS value voltage at the output of AC voltage controller increases, the brightness of bulb will increase. As the firing angle increases towards 180 degree, the brightness of the bulb will increase or decrease. As the firing angle alpha increases towards 180 degree, the conduction of track will increase or decrease. You have to assume the waveforms in your mind. We have already seen how track is going to work, right? We'll be giving firing pulse. It will operate both in positive and negative half cycle. So when the firing angle increases towards 180 degree, whether the conduction period of track will increase or decrease. Work done by the track will increase or decrease. Did you get the question? When I increase firing angle alpha towards 180 degree, whether the conduction period of track will increase or decrease. Bairegowda. No one has any idea. What I am asking? When, okay, this is the supply voltage. Now if I give firing angle at this point, what will be the output voltage? The output voltage will be like this. Okay, if I give the firing angle at this point, the waveform is going to be like this. Now in which case, whether in this case alpha is more, alpha 1 is more or alpha 2 is more? Alpha 1 is more.
Alpha 2 is more.
Alpha 2
Alpha 2
is
is more.
alpha 2 is more. Alpha 1 is less. That means alpha 2 is nearing 180 degree. Alpha 1 is greater than alpha 2. Right? Now, when alpha 1 is given to the track, whether its conduction period is more, or when alpha 2 is given, the conduction period is more. Conduction period in the sense on period of track.
During alpha 1.
During alpha 1, the on period of track is more because I am firing track at this moment itself. From this period to this period and from this period to this period, the track is in conduction. Whereas in this case, only between this duration and this duration, the conduction period is there for track. As alpha increases towards 180 degree, the conduction period of track will reduce. So the work done by track is reduced. When work done is less, the output will be less. So the illumination across the bulb will be reduced. So like this, by varying the value of alpha, we can vary the RMS voltage at the output of track, at the output of AC voltage controller. Okay, when the AC voltage at the output of, when the RMS value at the output of AC voltage controller varies. The illumination across the incandescent bulb varies. This we are going to observe. Then we are going to make a note of the RMS values across R and RL load, and we are going to plot the graph. Okay, that's the third thing. So what is the first thing that we are going to do? We are generating a control pulse using diac, and using that control pulse we are turning on track. By varying the firing angle, the output of AC voltage controller can be varied. Thereby, the illumination across the incandescent bulb can be varied. This we are observing. And for R and RL loads, we are noting down the RMS voltage values. How you can note down RMS value voltage across bulb? How you can measure RMS value across a bulb? How you can measure RMS voltage across a bulb? Which instrument do you use to measure RMS voltage across a bulb? You have already used this instrument, so I'm asking you. Gomate, which instrument you use to measure RMS voltage across a bulb? Okay, if it's a resistor, which instrument do you use to measure voltage? To measure RMS voltage, which instrument do you use? Anushri? Which instrument do you use? Navya? Nischal?
Yes, ma'am.
Yeah. Which instrument do you use to measure the RMS voltage across a bulb? ಇದೇನಾದ್ರೂ ತುಂಬಾ ದೊಡ್ಡ ಕ್ವೆಶ್ಚನ್ ನಿಮ್ಗೆ
DC voltmeter.
Voltmeter. We don't have voltmeters in power electronics lab. We won't use voltmeter is right answer, but we will be using multimeter by keeping it in AC mode. Okay, keep multimeter in AC mode and measure the voltage across load, that is bulb or RL load. You will be noting down the RMS voltage values and you will be plotting the graph versus alpha. So what you are going to plot? You are going to plot alpha versus VRMS. Okay, that's what we are going to do in this experiment. Let's look at the circuit. So this is the circuit what we have for AC voltage controller. Pavitra.
Yes, ma'am.
Okay, this is your circuit. I want you to simulate it and show it for the next lab.
Okay, ma'am.
Monday.
I didn't use diac and triac. I used diode and diac along with SCR.
Now I want you to simulate this circuit.
Okay, ma'am.
Okay, I'll explain the operation now. Based on that, you can perform it. Nothing, only the potentiometer is to be varied to vary the voltage across track and load. Okay, I'll explain the operation now. You can pick up the same circuit and you can show the operation in next Monday afternoon's class. Fine? Okay, first let me explain you the operation of this circuit. Okay, now you can observe the circuit. We have 230 volt supply and we have an isolation transformer. We have a switch connected here. This is only for protection purpose. Fuse and switch, what we have here. Fuse and switch, what we have here is only for protection purpose. This is the voltmeter which we have connected to measure voltage across bulb. Okay, we won't be connecting the voltmeter here. We will be using multimeter. Or we can go for digital meter. We have digital meter. We have either that or multimeter. We will be using to measure voltage across load. Okay, now this is connected to bulb. This is the R load. I have shown the circuit diagram only for R load, whereas for RL load, we will be connecting R in series with L. We'll be connecting R in series with L across these two terminals, across terminals A and B. Across terminals A and B, we will be connecting this load. Okay, as shown in the circuit, we'll be connecting resistance. You all have seen resistance. Inductance, we will be connecting. Okay, I can show you the inductance picture, how it looks like. Inductor for lab. One second. Let it come. Do you all have seen the inductor? Okay, the one what we use will be like this. The one what we use in lab. Okay, these are like this. Are you able to see, right? I'm showing one. I'm pointing to one inductor. Okay, these are our core type inductors. We won't be using this in lab. If we want for any project purpose, we can use. And this is how the lab the inductor what we use in lab looks like. Okay, the transformer also looks similar to this. You have seen the transformer in electronics lab, right? When we did the experiment rectifier experiment, when we did full bridge rectifier experiment, there he used a center tapped transformer. Okay, the same way the inductor looks, whereas we'll be having only two terminals because inductor will have only one winding, whereas transformer will have primary winding, secondary winding. So we had four terminals to outside. Okay, for inductor we'll be having only two terminals, so we will be using that inductor. We'll be using that inductor. Okay, next we have triac. Then the control circuit. This is the control circuit. Here, this is the control circuit. This is the control circuit, and remaining part is the actual circuit. Okay, when you redraw the remaining part of the circuit, here we have AC supply, and we have a switch. Then we have a bulb. Then we have track. Here we have the control circuit. Control circuit. This is how the actual circuit is. Okay. Since we have mentioned in the experiment name, we are generating control pulse using track. Okay, this is the track. Sorry, this is diac, using diac, right? This is diac, and the diac is used to generate control signal to track. Okay, now let me explain how the operation of this circuit will be. Now, what will happen first? During positive half cycle, we have positive and negative half cycle. During positive half cycle, current flows through this path. Right. Now what is happening here? The capacitor is charging. Like this also it flows. Now the capacitors are charging. Okay, DAC will come into conduction. Okay, can you tell me when a diode will come into conduction? When diode will come into conduction? What should be the voltage across diode to come into conduction? What should be the voltage across diode to come into conduction state, on state?
New voltage.
What is that voltage?
0.7 for silicon and 0.3 for germanium diodes.
0.7 volts. Okay, when the supply voltage crosses 0.7 volts, then only diode will come into conduction. Same way for diac also, it should cross certain voltage. The supply voltage should cross certain value, then only diac will come into conduction. Okay, it's not fixed for all the diacs. Like for example, if it is the case of diodes, all the diodes will be having in the same range, like 0.7, 0.71, 0.72, 0.69, like this. The knee voltage will be near or around 0.7. Whereas for diacs, it depends upon the construction. That's why we call diacs as partially controlled devices, because we will be having little control on turn on of the device. We can manufacture the device in such a way that uh, we can turn it on after certain level of voltage. If you want to turn on the diode after 15 volts of supply, we can turn it on. We can manufacture it in that way. If you want to turn on the diode after 30 volts of supply, like see, this is your AC voltage, right? Okay, your diac will turn on at this moment. As soon as 0.7 volts crosses, diode will come into conduction. Whereas diac, you can manufacture in such a way that if you wish to turn on diac after, let's say, 30 volts, you can manufacture diac according to your requirement. If I want to turn on the diac after 15 volts, I can manufacture it according to the requirement. So the diac what we are using in lab uh, turns on when the supply voltage crosses 30 volts. This is also one bypass question you can note. Okay, when the supply voltage crosses 30 volts, then only the voltage across diac terminals, if it's greater than 30 volts, then only diac will come into conduction. So now what is happening during positive half cycle? The current takes this path and the capacitor starts to charge. Once the capacitor crosses 30 volts, then the diac will come into conduction. Now, the charging of capacitor depends on what? The capacitor can charge at a faster rate or it can charge at a lower rate. When the capacitor charges fast, charging of capacitor depends on which parameter? Charging of capacitor, voltage across capacitor depends on which parameter. What is formula for voltage across capacitor? What is formula for voltage across capacitor? Manjesh? What is formula for voltage across capacitor?
Ma'am, Q by C.
Q by C. We don't know any Q or Q here, right? Any other formula do you know? Prithvi?
Only that, ma'am. Q by C.
Q by C. In ECA you used Q by C only for the voltage across capacitor. In electric circuit analysis, did we use only Q by C for voltage across capacitor?
I think 1 by C dV by dt.
1 by C integral I dt. 1 by C integral I dt gives you the voltage across capacitor, right? Here current is the main parameter. Okay, the charging of capacitor depends on what is the rate of change of current. How much current is flowing through the capacitor. Okay, if you keep the resistance at a high value, okay, if the variable of this resistance is kept here, the entire resistance is included. So the current flowing through the capacitor will be less. So the capacitor takes more time to charge. So the alpha will be delayed. Alpha will be delayed. It will be nearing 180 degree. If the resistance, the variable point of this resistance is kept at this point, the resistance offered by this path is least. So the capacitor charges at a higher rate and alpha will be nearing to 0. Alpha will be nearly equal to 0. Did you get my point? How we are varying alpha, how control signal is generated here. Did you get or not? Do you want me to repeat? We already know the voltage across capacitor is given by the formula 1 by C integral I dt. What it indicates? It indicates how much current, depending upon the current flowing through the capacitor, the voltage across capacitor will be decided. Okay, if the current flowing through the capacitor is at a faster rate, then the capacitor charges at a faster rate, then alpha will be, then the capacitor voltage will reach 30 volts at a faster rate. Then alpha value will be nearing to 0. Then the diac turns on at a faster rate, then alpha will be nearing to 0. If the resistance is more, then the current flowing through the capacitor will be less. Capacitor takes more time to charge, then diac will take more time to turn on or forward bias, then alpha will be delayed. Okay, by varying this resistance, we can vary or we can control the current flowing through the capacitance. Thereby, we can vary firing angle alpha. Is that clear? Okay, let's try to do it once again. Right, during positive half cycle, what will happen? Current takes this path, switch will be closed, so current takes this path. Now the capacitors C1 and C2 will charge. When the capacitor voltage reaches 30 volts, then diac will come into conduction, and when diac comes into conduction, the pulse reaches the control terminal gate of triac, and triac will come into conduction. Then the current takes this path and it closes the loop. Now, what's the point here is how to vary firing angle alpha. Firing angle alpha can be varied just by varying the potentiometer present here. Okay, when the potentiometer is kept at this point, the entire resistance is covered in the path. So current takes this path. So the entire resistance is covered. So the current flowing through the capacitance is less. So the capacitor takes more time to charge. So the diac will be delayed in turning on process. So what will happen? Alpha will be delayed. Alpha will be delayed when potentiometer is at position A. Alpha will be delayed when potentiometer is at position A. When the potentiometer is kept at position B, the resistance offered by the path is least, therefore more current flows to the capacitor. Capacitor charges at a faster rate, diac turns on at a faster rate, and alpha will be nearing to 0. So now what we can do, initially we can place the potentiometer at position B. First, place the potentiometer at position B. Note down the RMS voltage across the load and alpha by looking at the waveform. Okay, by looking at the waveform itself, you can decide what is the value of alpha. Now tell me, in this circuit, is it possible to get a firing angle alpha equal to 0? Think and tell me, is it possible to get alpha equal to 0 with this control circuit?
No, ma.
Because diac takes certain time to turn on. Okay, this is the disadvantage of this analog circuit. Okay, if it is digital circuit, we won't have this disadvantage. Just by going with 0000 binary code, we can generate firing angle alpha equal to 0. So this is one of the one more Viva question. What is the advantage of digital control circuit over analog control circuit? Okay, in analog control circuit, due to devices like diac, resistance and capacitance, the firing angle what we achieve won't be accurate, and the range of operation will be limited. Here we won't get the complete range. 0 to 180 degree we won't get. The alpha range will not be with complete 0 to 180 degree. Okay, it will be either at 10 degree, 15 degree it will start, and even it won't go till 180 also, it will start at 160 or something because of the delay in the elements here, delay in the diac, delay in capacitor. So one point what you can remember is when it comes to digital triggering circuit, the advantage is the range of operation what we get for circuit is more. Whereas for analog circuits, the range of operation what we get is less, because we are using elements like diac, capacitor and resistance. They take some time to charge and to turn on. Because of that, the alpha will be delayed. So nowadays in all practical devices or practical systems, they are going with digital control circuit, and only in few day-to-day base practical circuits, if you want to test the control circuit, if you want to test the device, there only in those cases we are going with analog control circuits. Okay, this is all about track DAC combination and how we are going to generate firing pulse, how we are going to control the illumination here. How we are going to control the illumination across the bulb? By varying what parameter we are controlling the illumination across bulb? Karthik? Karthik? By varying which parameter we are varying illumination across the bulb? Rakshit?
Yes, ma'am.
Yeah, by varying which parameter we will vary illumination across the bulb?
Current.
Current. By varying current, we can vary
Yes, ma'am.
the charging time of capacitance, thereby the alpha can be delayed. So the final parameter is alpha. Okay. By varying potentiometer, we will vary the current, thereby the capacitor charging time will be delayed or varied, thereby alpha will be varied. So the base parameter is current and the parameter which we can note down is alpha. Then in place of RL load, what we will be using is the practical inductor and resistance. We will be replacing the practical inductance and resistance will be replacing with bulb, and we will be noting down the values. Okay, now during negative half cycle, how this is going to behave is, during negative half cycle, here minus will be there, here plus will be there. So current takes this path. In this case, the charged capacitor will discharge and the current takes the reverse direction. Okay, current starts to flow when the capacitor voltage goes below minus 30 degree, minus 30 volts. When the capacitor voltage goes below minus 30 volts, then diac comes into conduction. Then the current takes the reverse direction and track will come into conduction. Now what we are noting down here, we are noting down voltage across bulb RMS value, and we are noting down alpha from the waveform. We will connect oscilloscope across bulb and we will connect multimeter also across bulb. From CRO, we will be measuring alpha, and from multimeter we will be measuring VRMS. Okay, we will make a tabular column like this. Alpha and VRMS. We will be connecting both oscilloscope and multimeter across bulb. From oscilloscope we will note down the value of alpha. From multimeter we will note down the value of VRMS. We will vary the rheostat from B to A. When rheostat is placed at position B, what is the value of alpha? You will note it down from CRO, VRMS, you will note it down from multimeter. Then you will vary rheostat away from B towards A. Then you will get one more value of alpha from CRO and you will note down VRMS value from multimeter. Okay, you will get a better idea when you see simulation next week. That's all we have for today's session. Do you have any doubts? And when it comes to tabular column, this is the tabular column. Alpha will and VRMS we will be noting down for both R load and RL load. and this is how the waveforms looks like. This is for R load, this is for RL load. Okay, during for R load at alpha, we are giving the firing angle. So this is the voltage that appears across the load. Okay, you can see, right? The second one is the voltage that we get across the load. Okay, at point alpha, we are turning on the track. So the voltage across track goes to 0. This waveform shows voltage across track. One second. This waveform shows voltage across track. This waveform shows voltage across load. Okay, until alpha, track is in off state, so supply voltage is appearing across track. When you give firing angle at alpha, track goes to on state, so voltage across track goes to 0 and supply voltage appears across load. During negative half cycle also same thing will happen. Okay, till alpha, track will be in off state, so the negative supply cycle will be appearing across track. Once the track goes to on state, the voltage across track will be 0 and the voltage across load will be same as the supply voltage. In case of RL load, during the on period of track, the inductor gets charged. That will be discharged during the negative half cycle. Okay. See, we can see from the circuit. If I place a RL load here, from alpha to pi, the current will be flowing through the load. From alpha to pi, current will be flowing through the load. See, this is the duration. From alpha to pi, current will be flowing through RL load. This is the current waveform as I showed. This is the current waveform. If you observe from alpha to pi, the current is flowing through RL load. At this point, current, once the supply voltage crosses 0, current through the inductor, suddenly it can't change. It can't go from this value to 0. So what will happen? Inductor starts to discharge slowly. Okay, during this process, track keeps the supply voltage in loop. Therefore, the supply voltage appears across the load. Okay, this is the same case as we discussed in PE class, last PE class. Diode bridge rectifier with RLE load we discussed, right? Same case is coming here. Okay, from alpha to pi, current flows through RL load. As once the supply voltage crosses 0, the current flowing through the inductor can't go to 0 suddenly. So the inductor starts to discharge the energy. Okay, during this process, the current starts to reduce and in some point it goes to 0. Okay, during this interval from pi to beta, the track, okay, we can look at the circuit. The track will remain in on state and it will be connected to source. Due to inductance discharge, the current through the track will be greater than holding current. So the supply voltage will be appearing across the load. So that's why the waveform across load is like this. We'll be having negative spike. During this period, pi plus alpha to 2 pi also inductor will charge and during positive upcycle it will discharge. This is the waveform for voltage across track. And this is all about the AC voltage regulator using track diac combination. Next, what we have, waveforms we did. Then analyze and observe the change in waveforms as the value of inductor decreases and increases. Okay, when you perform the experiment practically, you can vary the value of inductance. Okay, in the same inductance, you will be having multiple options like you can go with 1 Henry, 2 Henry, 3 Henry, 4 Henry. You can try out all the values of inductors and you can check how the waveform across the voltage waveform across load is changing, whether the voltage spike appearing across load is increasing or decreasing. Okay, all these things you can observe. Next question is obtain constant voltage across the load using AC voltage controller with variable input voltage. Okay, you can keep any variable voltage. You can keep a transformer at the input side and you can vary the input voltage, and by varying firing angle alpha you can try to maintain the output voltage constant. Okay, this is one questionnaire what you have for this experiment. You can try out these two things in lab. Okay, that's all about this experiment. Do you have any questions? Students, do you have any questions? A reply. If not, we can close the session. We can continue in next class. Pavitra, you'll be doing simulation in next week, right?
Yes, ma'am.
Yeah. I hope no one have any questions. We'll continue into next class.
Okay, now let's see how to do the connections for single phase AC voltage controller. This is the circuit diagram of single phase AC voltage controller. This is the circuit diagram of single phase AC voltage controller. First, we are taking 230 volt supply. Okay, this I have taken the power plug 230 volt supply. We are not using the transformer. I have directly given the connections to fuse and capacitor. From positive, it's going to fuse one end. From fuse other end, it's going to switch. From switch other end, it's going to bulb load. Then from load bulb other end, it's going to empty 2. From empty 2, it's coming to variable point. Then from fixed, it's going to capacitor. From capacitor, it's going to resistance 6K8 resistance. From resistance other end, it's going to capacitor, another capacitance. From that same point, it's going to diac. From diac other end, it's going to gate. Now this capacitor is shorted. Then from triac, it's coming to this junction, capacitor junction. Okay, this is how the connections are made. And in this case, we have taken resistive load, that is bulb load. And since it is 230 volts supply we are using power scope. The operation of power scope is similar to normal scope. The only difference is this power scope can measure up to 600 volts peak to peak. Okay, how to take the readings is 1 division into this scale into 100. This is the multiplication factor you have to follow. If your signal is within 1 division, it is 1 into the scale is at 1. 1 into 1 into 100 volts. If your signal is within 1 division, it indicates 100 volts. And this is for channel 1, this is for channel 2 y-axis modulation, and this is for x-axis modulation. Now let's switch on the supply and we'll see how to obtain the readings. What we are going to do in this is a AC voltage controller which converts AC voltage to another AC voltage. I am giving 230 volts fixed RMS voltage. At the output side, we are going to observe as the firing angle varies, how the output RMS voltage can be varied from 0 to 30 volts. Now let's see the operation of AC voltage controller. Let me turn on the supply. I have kept the alpha to minimum value. When alpha is kept at minimum, alpha equal to 0, the entire supply voltage will be passed to the output. So the RMS voltage I am getting here nearly equal to 230, that is 229.3. It's nearly equal to 230. And you can observe the load voltage is nearly sinusoidal in nature. Now, how to take the reading here is, here this is 1 division, 2 divisions, 3 divisions, 3.1 or 3.2 it is showing. 3.2 into 1 is 3.2 into 100, so around 320 volts peak value you are getting. 230 volts is the RMS, 320 is the peak. Now, as I vary alpha, the conduction period is reducing. The conduction period is reducing. Wherever you are seeing the waveform, that portion is the conduction period of track. Now I am reducing alpha, the conduction period is reducing, so the voltage is reducing, output voltage is reducing completely. I kept alpha at the maximum value, whatever it is possible with this circuit, so the output voltage is nearly equal to 18 volts RMS. So now how to note down the readings alpha versus VRMS is, Alpha you need to measure from CRO. Okay, from CRO, this is the zero crossing point. This is the zero crossing point. Okay, this is complete positive half cycle. The zero portion, whatever you are seeing, is your alpha. When time scale is kept at 5 milliseconds, one small division indicates 18 degrees. So this zero portion is covering 36 degrees. So alpha is 32 divisions. So it is 18 into 2, 36 degrees. 36 degrees, when alpha is 36 degrees, output voltage is 205 volts. Now, when alpha is kept at 90 degree, when alpha is kept at 90 degree. Okay, two divisions cover 180 degree. So one division is short here or 0 volts here. So it becomes 90 degrees. When alpha is 90 degree, output voltage is 113. Now I am going to increase alpha further. When alpha is 90 plus 36, the output voltage is 21. When alpha is 180 minus 36, the output voltage is 18 volts. Okay, this is how we can perform AC voltage controller experiment. We can note down the values of alpha and VRMS. You can do the plot alpha versus VDC, and you have to draw the waveform for voltage across SCR. Now we'll see how to perform inductive load. Okay, we have AC voltage controller for both R load and RL load. In case of RL load, we are going to connect inductor in series with bulb. Okay, let's see that how to do the connection. Let's switch off the supply and remove the power plug. Okay, this is the inductance, variable decay inductance. Now what I'm going to do is, I'm going to remove this connection, which is at MT2. Okay, this connection is going to MT2. So I'm going to remove this connection. I'm going to remove this connection, which is at MT2. And I'm connecting this to inductor. Now from inductor, I'll go back to MT2. This is called as series connection. From inductor, I'll go back to MT2. I'll go back to MT2. So from switch, it's coming to bulb. From bulb, it's coming to inductor. From inductor, it's going to MT2. Now let's switch on the supply. Now you need to observe the voltage across these two terminals. First terminal is from switch and second terminal is going to MT2 at this point. Now let's increase the inductance value. Yeah. Now you can observe the inductor is slightly charging and discharging. This small line, whatever it is, whatever you are able to see, is the inductor discharged portion. The ideal waveform will be like this. The ideal waveform will be like this. During this period, inductor will charge. During this period, inductor will discharge. But the inductor value is very low, so you are not able to observe the discharge portion much. In this case also, what we need to do is, same way you have to vary the alpha by varying the variable part of rheostat and by noting down the alpha from the waveform. Now it is 18 into 3. The voltage is 197 volts. Same way, when alpha is equal to 90 degree, it is 121 volts. When alpha equal to, further if you increase, the voltage will reduce. This is how you can note down the values of alpha and VRMS for both R load and RL load. What we understood from this experiment, as alpha varies, how the output RMS voltage can be varied is demonstrated in this experiment.